Next up, we have Maya Stedman, bioinformatics scientist at Elucidata. Maya is a bench scientist and a bioinformatician who has worked on novel drug discovery projects, including 3 clinically approved compounds. For her talk today, she will be exploring how you can apply augmented intelligence to ensure data quality. Her session will also demonstrate Elucidata's data quality assessment approach. Take it away, Maya.
Hey, everyone. Let me just pop my slides up here. Okay, everyone can see my screen?
Yes.
Wonderful. Okay, so again, my name is Maya Stedman, and I'm a bioinformatics scientist here at Elucidata, as Miriam so kindly introduced me. Today, I'm going to talk to you about how we are applying augmented intelligence to systematically improve data quality. Now, most of you are probably familiar with the term artificial intelligence, but augmented intelligence is slightly different. Both techniques rely on machine learning and have the same goal, but they accomplish that goal in different ways. Artificial intelligence operates completely independent of a human, while augmented intelligence is designed to improve human decision-making. When you should use artificial versus augmented intelligence is driven by the use case. And since assessing data quality is extremely context dependent, we have found that augmented intelligence is more appropriate. So let's talk a little bit more about the context. A basic example of machine learning is the NLP model used by Grammarly for their grammar checking application. Like all internet companies, Grammarly has access to billions of data points to train their models, many of which are provided by me for Grammarly. This large sample size makes it fairly easy for them to train their models without much concern for the quality of each individual data point. But in our field, we don't have the luxury of enormous sample sizes. More typically, the data sets available to us have sample counts in the hundreds. When the number of data points available is this small, any reduction in quality can lead to a decrease in model accuracy. So we have 2 options to improve the accuracy of our model. We can either generate more data or clean the data points that we have. Now, it's not always possible to generate more data for a number of reasons. This could be due to the cost associated with generating more data, both in terms of time and money, or the fact that newly generated data will also introduce more heterogeneity into the situation, which isn't always what we're looking for. So when generating, or even when generating more data is an option, it's not our most efficient one. Taking a data-centric approach means that we focus our efforts on providing high-quality data that can properly train the model instead of spending the time trying to improve the model while our inadequate data is left unchanged. But before we can start improving our data set, let's take a step back and we have to understand the factors that contribute to data quality. First, there are intrinsic traits, which are inherent to the data, and these can generally not be changed after the data has been generated. Intrinsic traits include experimental design, measurements, and metadata records. In an ideal world, all the intrinsic traits would be high quality from the start, but we all know that this is rarely the case, unless I'm doing the experiment, and reality falls short. So we have to focus on the extrinsic traits to improve the overall quality of our data set. Now, extrinsic data quality traits are affected by the systems and the processes that interact with the data after it's been generated. These traits can actually be greatly improved through curation. And when we're thinking about how to improve the overall quality of a data set and the different parts of the experiment that you could focus on, the metadata understandably may not be the first thing that comes to mind. But when we look at the tools in our arsenal, it becomes clear that the biggest gains can be made in this area. For example, poor experimental design will affect the desired outcome of the experiment, and I may not be able to answer my original question, but the resulting data can still be used for another purpose. So by shifting the question or asking it in a slightly different way or asking a different question of my data set, I can make a small gain in the data quality here, repurposing my data. Poor measurement quality can't really be recovered from. Normalization is only going to get you so far. And if you don't trust the accuracy of the measurement, you're not going to waste your time using that data set. So again, assuming the best case scenario, we can only improve our data slightly through things like normalization and batch correction. Likewise, poor metadata quality, as I pointed out, can severely reduce the usefulness of a data set, and it can ruin model accuracy. However, as long as there are unstructured records, like the text of a publication or an ELN, the metadata can be improved at any time. And we already know that this works. Improving the accuracy and completeness of metadata by cleaning the labels has been shown to improve model performance more efficiently than increasing the sample size. So let's go back to the scenario I mentioned in the beginning and elaborate on how we can reduce the noise in a data set, or in other words, clean and link the data. Data is often stored in complex folder structures that are organized by the date presented or by the instrument used to generate the data. Now, I know I was guilty of this when I was in the lab, and I bet many of you are thinking about how your data is currently being stored and what the folder structure looks like. So hopefully this is a familiar situation for everybody. The lack of a consistent structure always leads to an inevitable loss of value. And I'm talking about the consistent structure within an organization, or even sometimes within teams themselves. That loss of value can come through the time trying to locate the data, needing to reprocess the data when you find it, or even going as far as needing to repeat the experiment entirely. And even when the data has been properly stored, the equally valuable metadata for that experiment is likely stored somewhere else. This would also need to be located, reprocessed, or regenerated. So our example data set here that I have depicted on this little graphic is a real data set. It's GSE 109211. It's a gene expression profiling data set collected from HCC tumor tissues of patients. The raw data and the metadata file were both downloaded from GEO, and most of you are probably aware of the state of affairs on GEO. So what we have found is that in any given data set, about half of the annotations are missing, and of those that are present, only about 2% are harmonized. And what we mean by harmonized is you may have one sample that's labeled as breast tumor and another that's, or I should use HCC, seeing this is an HCC experiment. Anyway, you might have one that was labeled as breast tumor and another that was labeled as breast neoplasm. And where we can understand the context of those two labels and know that they both probably mean the same thing, it makes this data not machine readable, because they would be two different labels. So we're talking about harmonizing those and making sure that all of those tags are consistent. So given that this is the state of metadata today, the question that we at Elucidata asked is, what can we do to make these data more usable? The approach that we chose to use was a data-centric NLP model to fill in the annotation, those that are missing, and ontological libraries to standardize the metadata terms. We're using data engineering as well to convert everything into consistent file formats. So we've largely automated the standardization and harmonization pieces using connectors. And connectors act as scientifically validated pipelines that use, again, our data-centric NLP models, so PolyBERT, to harmonize the data with little human intervention. So let me walk you through how this process works. To start, you decide what data model your ingested data should conform to with our schema builder application. In this app, you create some basic rules, for example, that the abstract field can only have a text value. Once you're satisfied with the schema, you can validate this final table and insert it into an omics atlas, which is where your data is housed on Poly. With the schema in place, you can start running the connector. Data ingestion through connectors is a simple one-command process over a programmatic interface. You pass a few parameters such as the connector type, the dataset ID, and where you would like the data to be pushed. With these, you create a JSON file and can start the ingestion process. Users can also check on the status of their ingestion through a monitoring dashboard. On this dashboard, you can check that the data conforms to the schema that you previously defined. It lets you keep track of the data sets that are in the queue, as well as you can have a view of all of those that have completed ingestion onto your omics atlas. It also gives you logs of the job to ensure that everything is going well. So if anything's failed in the process, it shows up on the log and you can take actions to remedy the situation. All the data sets that pass through the same connector will have the standardized format, and the metadata will be harmonized across the entire Omics Atlas. So it's not just one data set. Everything in that Omics Atlas is going to be harmonized in terms of metadata. The next step is our validation layer. So to ensure that all the required metadata fields have been filed and annotated correctly, we have a built-in validation layer that performs the metadata checks at the dataset and the sample level. So the top level of your file, and then the individual rows or columns within that file. The validator looks for concordance in the schema first, which verifies that the column type matches the field value. So for example, if your column type is string, then the field value must be a string. Next, the validator checks that the field values are included in one of our ontological libraries. For example, the disease listed is actually, in fact, a mesh disease term. Mesh is the ontological library that we use for diseases. Then there are field-specific checks, such as that the date is greater than 1900 and prior to the current year. Another example is that tissue column should contain a tissue and not drug. Finally, the validator checks for logical concordance, meaning that the field value matches with the column logically. Sounds obvious enough, right? So if the column is tissue and lung is the field value, it'll pass. But if the column is tissue and lung neoplasm is the field value, it'll fail. And that's because although lung neoplasm is a proper mesh disease term, it doesn't logically pair with the tissue column. It belongs in the disease column. So finally, if you want to curate fields that are extra and they're outside of what Poly has a defined curation model for, there is the metadata annotation process that can be performed on our curation app. This app operates on the principles of active learning. So what you do is you define a curation configuration and start manually annotating a data set. Over time, the model learns and gets more accurate, and it even predicts the values by itself for the next time with the greatest confidence score. So you can scale up your curation process and go faster. In the end, this is what an index file looks like in an Omics Atlas. Each file is in a standardized format. It's complete with the data matrix and the metadata in one place, right on top of each other. And that they've all been harmonized according to those ontologies that we set right in the beginning. And it's done again on 3 levels. So data set, the top level, sample, and feature level. And now the harmonization on all 3 levels is what powers our amazing search capability within an Omics Atlas. So because you can search on all 3 levels and subset the data as you please, you're now empowered to ask really complex and specific queries, such as find me all data sets where the disease is breast neoplasm that have both healthy and diseased samples within that data set. And now the next layer down is you can even pull out a specific set of features. So you could say have a panel of 10 genes and ask for, you can go right into all the data sets that are in that Omics Atlas and pull out a subsetted table that only have those 10 genes and that only meet those previous requirements very easily. And then that subsetted data table can be taken on for any downstream analysis that you have in mind right on the platform. So here we have our whole data-centric platform in one neat little graphic. Poly provides centralized data management where the process data and the metadata are stored together. Our connectors are scientifically validated ETL pipelines that continuously, once they're implemented, they're continuously gathering data from various sources, and they curate it by processing it into the standardized schema and harmonizing the metadata. We've actually tested our models against human curators, and the F1 scores show that our model is nearly as accurate as an expert. Additionally, our model-assisted curation leads to higher throughput, the ability to scale to hundreds of curators, and our new model development time is lower due to that active learning process. Altogether, this allows us to curate data at a rate that's 10 times faster than our industry standards. So the ingestion infrastructure then pushes all the data into an omics atlas where it's indexed. And as I just went over, that's what is allowing us to do those powerful searches, right? So the data infrastructure on Poly makes the data findable for easy use and reuse in reports and insight generation. Omics Atlas becomes the source of truth for your data, and it allows users to set up seamless data streams from the harmonized atlas to downstream applications and pipelines that you can host right on the Poly platform. So with that, I want to thank you all for your time and giving me the opportunity to talk about this. I absolutely love talking about metadata, so I look forward to your questions. Thank you.
Thank you, Maya. We have a couple of questions, but we're a little bit short of time, so I'll just pick two and we'll go forward with those. The first one is, what is the difference between augmented intelligence and AI?
Yeah, so this is a great question, and I have to tell you it was really hard for me to keep them straight when I was preparing for this presentation. The temptation is to just kind of lump them into one. But the main difference is artificial intelligence is meant to operate completely independently of a human, right? So you train the model in the beginning, and then the whole process end to end should be done with no interaction. Augmented intelligence is specifically designed to improve human decision making, right? So our curation app is a perfect example of augmented intelligence. We're working alongside the model, and it's saying, do you mean this or this? And our curators can then either agree or disagree with what the model has suggested. And with that, the model will learn. So it makes our lives easier because we can curate faster because we're being suggested instead of having to figure out, oh, is this a drug or is this a tissue? That's a bad example. You would obviously know a tissue from a drug, but say you don't. It gives you like, I think this is a drug, and you can be like, yeah, actually that is a drug. Good job, model. Good job, Polybert. And it's like, great, I got it right. So now it has an extra data point, it learns, and you both move faster. I've just completely anthropomorphized our Polybert models.
Good explanation. Awesome. Thank you.
Yeah.
And the second question, can you explain extrinsic traits with examples?
Yeah, extrinsic data traits are actually, it's a kind of it's a nebulous concept. Intrinsic is really easy. When you think about the data, you're like, okay, these are the things that come with the data set. They're part of it. They're inherent. You can't have a data set without these things. But the extrinsic is, like I said, it's everything that you do to the data after it's been generated. So an example of this would be, I have my data file and it's listed as like cohort A, B, and C, right? So I can split my data and I can do an analysis with cohort A versus cohort B versus cohort C, but it doesn't tell me that much. By adding another layer of information, I've changed the data, so I've affected it. And that is now an extrinsic trait. It didn't come alongside of it, but I looked back at the context and I know that cohort A is actually normal in cohort B is diseased and cohort C was drug treated. Now, another example would be you want to do quantitation to your data, right? So you have raw counts and now you want to quantify them. So you have a standard curve and you do a calculation on top of that data. And you're changing the value of the data matrix. That process of quantitation is an extrinsic value to the data quality. The data didn't come with that quantitative value. You did it on top of that.
Awesome. Thank you. Thank you, Maya, for this elaborate session. We appreciate it. I bet the audience actually learned something from it.
I learned a lot too, so I'm glad to be here. Everything's been great. Thank you so much.
Thank you.